for now, it is my very great pleasure to be introducing our second speaker, Professor Andrew Gelman. Andrew needs no introduction to the statisticians who are listening to this. For those of you who are not fortunate enough to be statisticians, Andrew is Mr. Uncertainty. If you have ever taken a course in Bayesian statistics, or if you have ever taught a course in Bayesian statistics, you are likely to have referenced and cited Andrew's work. He is a very deep thinker, and thinking about uncertainty and communicating it is one of Andrew's passions. So I will, without much further ado, it is my honor and pleasure to introduce Andrew to you today. Andrew.
Thank you. It's a pleasure to be in Australia. I feel like I'm kind of ahead of the curve because people are always inviting me to speak places, and I said I didn't want to fly, so I'd give these remote talks. And it never goes as well as a real talk, but now they're all remote talks, so I feel like everybody else has been brought down to my level. So I'm very happy about that. This is a graph that appeared on the internet a few years ago. Someone had leaked it. It had been presented, that someone had shown it in a presentation for the FBI, in the United States. I'm sharing this this is sort of a horrific graph. If I'll give you a moment to soak it all in. Now, there's a lot of strange things going on in this graph. One of which is the idea that the Bible started out very violent in 3 BC. In 3 BC, I sort of think the only Christians involved were Jesus and Mary. And I guess if you've ever seen a little baby and the mother, you can believe that there was a little bit of violence going on. But nonetheless, it seems a little odd to me. As a statistician, this graph really bothers me because of the x-axis. Look at the difference between 610 and 622. That's as large as the difference between 3 and 610. So, but my point in sharing this is that graphics are an accepted form of communication. So it's not just people trying to convey interesting things, it's also people who are trying to spread hatred are using graphs also. So you kind of need to know, we need to have some understanding of statistical communication in any case, because people are going to be doing this sort of thing. I'll show maybe a more pleasant example or something I've been working on more recently here. So this is our forecast of the US elections that a colleague at The Economist magazine and a student and I set up. It says that right now our model thinks that Joe Biden is very likely to beat Donald Trump. It gives him a 90% chance of winning. This was an interesting example. When we released this forecast a few weeks ago, the probability was 84%. And somebody pointed out that although we were giving Biden an 84% chance of winning, the betting markets in Australia and in the UK were giving Biden something more like a 55 or 60% chance of winning. And we're very used to trusting the betting markets. So there's this idea in our society that markets reign supreme. But we were making the case that we actually think our forecast is better than the markets. So in order to, like, in some way, that's like a difference of opinion, right? Like they say, difference of opinion makes bets. If you believe our forecast, you can go in Australia right away and bet and make some money. I can't really do it so easily from the United States. But when we have disputes, we don't merely have to say we disagree. We can try to figure out where the disagreement occurs. So I was corresponding with a colleague who said that he thinks that our forecast should be much closer to 50-50. And I was like, 50-50, really? And he said, oh, sure, like, we don't know. There's a lot of uncertainty between now and election day. And so I think we should be more modest in our predictions. So then my response to him was, if you think that Trump has roughly a 50% chance of winning the election, then what is your probability distribution for his vote share? So this is the Electoral College. We have a complicated system in the United States. Let me scroll down to the popular vote. So right now, we predict that Biden is going to get 54% of the popular vote and Trump's going to get 45%. We're ignoring votes for third parties. And then there's these dots represent 95% uncertainty intervals. So we think there's actually like something like a 97% chance that Biden gets at least 51% of the vote. Because of the way that the US distributes the votes in the election, and because of certain imbalances in where people vote, our estimate is that Biden needs over 51% of the vote to win the election. That is, if Biden gets 51% and Trump gets 49%, Trump would probably still win with the way they count the states. Anyway, the point is that I'm saying that I think Biden's going to get 54% of the vote, and I think it's very likely it's going to be between 51% and 57%. So if you want to say that Trump has closer to a 50% chance of winning, you have to either say that you think there's a lot more spread, a lot more uncertainty in the vote, or you have to say you don't really predict that Biden's going to get 54% of the vote. But you kind of have to do that. So my point, I have kind of 2 points of this story. One is that we're talking about communication, and we have a number of ways of communicating the results. So I'll scroll up and show you that, just to, just to demonstrate what we've done, because it's kind of cool and we put some work into it. People are reading it. The other reason is that forecasts, predictions don't exist in a vacuum. They exist within a web, a network of probabilities. So probability and uncertainty, we have a way of talking where we pull out one thing. What's the probability that the president of Syria is going to be out of there in the next 12 months, right? What's the probability that Vladimir Putin is going to choke on a chicken bone, right? We have all these things. Is an asteroid going to hit us? Like, what's the probability Australia is going to run out of water? Like, whatever it is. But these events are not independent. And the way we can understand our forecasts, our predictions, our uncertainties is to interrogate them. It's to take them seriously. So when I make a forecast, I take it seriously. I stand behind it. Well, I can be wrong. Standing behind it doesn't mean that I might be wrong, right? But I get married to my forecast, and yeah, I might get divorced later. I might have a prenup or whatever. But when I'm married to it, I want to really kind of respect it and go with it. So before going back to the forecast, I'll give you an example. This is one of my favorite probability examples. I have 2 random variables. One of them is the outcome of a coin flip. It's 1 if the flip is heads, and 2 if it's 0 if the flip is tails. It's just a regular coin, not a trick coin, 50-50, heads or tails. The real thing, right? Flipping a coin. The other is there's going to be a fight between the world's greatest boxer and the world's greatest wrestler, a fight to the death. And if the boxer wins, the random variable takes on the value 1, and if the wrestler wins, the random variable takes on the value 0. Well, I don't know about boxing and wrestling, so it seems like 50-50 to me too. But those are different things, right? One of them is a so-called aleatory uncertainty, a purely random uncertainty, whereas the other one is an uncertainty in the process. The second probability doesn't seem truly 50-50 in the way that the first one does. But how do you handle that mathematically? Like, one thing I could say is, well, that event of the boxer and the wrestler, it's actually, the probability is P that the boxer wins. right? But I don't know P. P could be anywhere between 0 and 1. I don't know P, so I'm uncertain about P. I give P a uniform distribution, and then the probability is a half. That doesn't really help me. It's still 50-50. P is unmeasurable, so I can't do anything with that. The way I can learn more, the way I can conceptualize, and people have had other ways, like how do you deal, they talked about fuzzy sets, upper and lower probabilities, like different mathematical theories for how do you distinguish between these two random events that are different, right? How do you deal with them? It's the known unknown and the unknown unknown. So I do think there's an answer to this. I think there is a distinction. So I'll tell you about that in a minute, but now let me go back and show you this thing again and brag about what we did. Okay, so first we did this. Now I'm guessing, since given the audience in this, you all are either happy that Biden has a 90% chance of winning according to this model, or you're unhappy that Trump's chance is still 10%, which is not 0. That's just the way it is. How do we think about this? I have great difficulty thinking about 95% intervals in political science, because we have presidential elections every 4 years in the United States. So that means your 95% interval should be wrong 1 time out of 20, which means 1 time out of 80. That means once in your life, right? So if you want to say, does Trump have a 1 in 10 chance of winning, you just have to go back 80 years and say, are there any elections where someone seemed certain to lose and they won, or certain to win or they lose, or there was a big difference? Like in 80 years, you know, that's 5%, sorry. So 1 in 10 would be 40 years, right? So in 40 years, all sorts of things can happen. One of my themes is that we demand too much certainty. So what everyone wants is the 95% interval with 95% coverage that is narrow. You want both. But like you can't, you know, like as they say in the computer business, blank, 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 pick any 2, right? It's the same thing here. You can't really, you can't, but that's what people want, right? That's the tension. That's the tension of statistics. Now, statistics textbook writers are bad people. I'm a statistics textbook writer. I'm a bad person too, right? We are bad people because what we do is we tell people stories of success after success. We'd be like, this would be like one of these books, like suppose you wrote a book like How to Street Fight. Get out there, act tough, man, you know, just get yourself out there. And if anyone comes close to you, take a swing at him, go for it. And then they have all these stories. I was walking down the street, this dude was mean to my girl. I took a swing at him. He ran away. One after another, story after story. I took a swing at him. I kicked him in the ass. You know, okay, great set of stories. You go out there and you read the book, and for a few days you're kicking everybody's ass until you run to someone else who read the book. And then there's like blood on the street, and it's bad news, right? This is what it's like when we write statistics textbooks. We have example after example where we do blah, 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 and the result's statistically significant, and we win. Blah, 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 win. You did it again. It's over and over. My books are the same way. It's terrible. We give this message, right? We don't have all the examples that fail. That's sort of boring. You don't want to hear about that, right? It's just to then people go and people like use our methods, and they come into this expecting success every time, right? Because we show them success every time. So they design studies and they think we designed a study to show blah, 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 blah. What's wrong with that? Oh, you already knew the answer. I guess you didn't need to do the damn study, right? Okay, there it is. We have some treatment and it's better than the alternative. Well, maybe it's not better than the alternative. Did you ever think of that, right? Well, we're not really training people to do that as statisticians. I think here's a situation where you really can control your uncertainty. You run a casino in Las Vegas, then you can really just make money, right? But if you have real world uncertainty, you can be wrong sometimes. And like the probability is supposed to help you. That's like probability tells you what could happen in the best case scenario, which is a start, right? Because if things don't work well in the best case scenario, you're in bad trouble. But it doesn't give you all the answers. So because of that, we need to tell rich stories. So when we talk about uncertainty, it's a rich fabric of uncertainty. We have to be world creators, right? Like, you know, like that book Dune, you know, the one, well, whatever, it's a famous science fiction book. The guy created an entire universe, right? Because it all had to fit together. You can't just, it's not about like sticking a spaceman into your current universe and having him fly around and like shoot people or whatever. It's about the entire web of connections. So we do that. So here's an example. The electoral college, so we have the electoral college votes. So we expect Biden will get 340, you need 270 electoral votes to win. There's uncertainty, now this would be if you ran our model, if you started our model in March. So back then we thought it would be very close because the economic conditions have changed since March, as you might have heard. I think in Australia, you guys completely eradicated the coronavirus, but here it's still running around, as you might have heard. So that's our time series. Then you can also look at his chance of winning, and you see it was, as of March, it was closer to 50-50, but things have changed. We have our simulations for the Electoral College. It has a funny distribution because the states are discrete. So if you win or lose a big state, it will cause big jumps in the number of Electoral College votes you win. Then we have the chance of Biden or Trump winning each state. This is hard for you in Australia to read. You all only have 6 states, but we have 50, so there's a lot more things to stare at. But you can see that Donald Trump is likely to win Texas and so forth and so on. We ordered the states. We have the popular vote, but then we have more. So you can look at individual states. So let's look, these are competitive states. So let's look at Arizona. So in Arizona, it looks like Biden is likely to win. We can look at the popular vote. Biden's predicted to get 51% of the vote in Arizona, but there's some uncertainty and so forth. So we have all that, and we have our source code. Look at this. So you can go run it yourself. Well, transparency is pretty important, right? So I was going to tell you this, how I resolved the boxer and the wrestler. And my resolution of the boxer and the wrestler is that, yes, they're both 50%, but they look different when I embed them in additional information. So let me imagine some more information on the coin flip. Like I flip the coin a whole bunch of times. I take measurements on the coin. I measure the relative humidity, all sorts of things. Pretty much no matter what information I get, that probability is still 50-50. Unless I actually take measurements while the coin's in the air. Anything short of that, and it's going to be 50-50. There's just nothing, it doesn't matter if the coin has like printed a funny way. It doesn't matter what the edge of the coin looks like. If I flip the coin in the air and catch it and read it, it's going to be 50-50. With a boxer and the wrestler, though, I can gather information. I could do some trial heats. I could hire, if I have enough money on the line, I could hire like an okay boxer and an okay wrestler and gather some data. I can imagine learning about it. So I could embed it. So when I say mathematically, when I say the probability of the coin is really 50-50 no matter what, and the probability of the boxer and the wrestler is an uncertain 50-50, mathematically that means that as I condition on more information, the boxer wrestler probability can vary, whereas the other one doesn't. And that will come up in the election forecast too. What information would it take to make that probability go down to 50-50? So one reason the probability is what it is based on the opinion polls, because Biden is doing well in the polls. But another reason is that we have a forecast based on economics and we have a forecast based on economic and political history. So if I show you this again, now let me go back. We have a document summarizing it. I think it was here. We have a pretty picture. Here, this is from 1992. So here's an example where there is a prediction based on the fundamentals, which is the economy and the political conditions, and that changes a little because the economies change and political conditions change, but the polls jump all over the place, but then when you put them together, you get a very stable probability. We had another, oh yeah, is this, wait, we have a very pretty picture. Shoot, it's not here. It's okay. I'm not going to try to search through. We have some other pictures showing the historical basis. It's been said that your most important collaborator is yourself 6 months ago, and she doesn't respond to emails. And that's super important, that communication is not a frill. Okay, so I think communication is thought to be a kind of soft skill, right? So it's just like in politics, right? Like the economy, that's this soft thing, soft power. It's not as important as like being able to drop hardware in people's heads. Well, maybe it is so important, right? And similarly, well, communication, it's not just this soft thing. It's not just, I think it's typically presented as the purpose of communication is you have some great insight and you want to convey it to the world, right? Like storytelling, let's have a storytelling workshop and get some storytelling expert to come in and tell us some stories. And then they're going to tell us how we can tell stories, because people think in terms of stories, right? So you should be telling people stories. It's so patronizing, right? Like, oh yeah, we're intelligent, rational people, but other people, they're idiots, right? Oh yeah, so people think in terms of stories, so you have to baby them along. So come up with a story to sell your research, right? Like tell a story. It's just, okay, that's not what it's about. Okay, we understand things in terms of stories. Now, there are two important things about good stories. The first is that it's anomalous, and the second is that it's immutable. By anomalous, I mean a good story has a surprise, right? A story is not like I went to work one day and said hi to everybody and then I came home. Well, that's not a good story unless on the way home I got run over by a bus. That was a surprise. You didn't see that coming, did you? Huh? Pretty good. Huh? So it's anomalous. The other thing that's important of a story is that it's immutable, meaning it has truths that you can't get around. So stories are important to us. I've told you a bunch of stories, and these stories had little surprises, but these stories are also true. If I was allowed to make it all up, I couldn't learn anything, right? You can't learn anything by just repeating. If I fit a statistical model, I can create simulations from the model and look at them. That helps me understand my model better, but it doesn't help me understand reality better. I understand reality by comparing my simulations to the model. So good stories have this surprise in them. But there's a funny paradox. I'm going to end with this paradox. I have another like 10 hours worth of material for you where I didn't have a chance to get to. I'm going to end with a paradox. And the paradox is this: good stories are surprises. That's how we learn. We learn from surprises. Yet in statistics, we're told to look at representative samples. So the surprise in the story is because things are not representative. So that's something you can kind of chew on your own time. So that's it.